What if the impossible wasn't just imagined, but engineered into reality? Picture this for a moment. A high-speed train, not racing across plains or slicing through mountains, but gliding silently beneath the ocean floor. No sky above, no horizon ahead, just steel, speed, and human ambition pushing through the depths of the sea. Today, we dive into a project so bold, so technically demanding, that many experts once dismissed it as pure fantasy: the construction of the world's longest undersea high-speed rail tunnel. In recent decades, China has transformed itself into a global powerhouse of infrastructure. From vast highway networks to record-breaking bridges, its pace of construction has been nothing short of relentless. But now, the country has set its sights on something far more ambitious, connecting the islands of Zhoushan to the mainland city of Ningbo through a massive undersea link. To make this vision real, China has proposed an investment of approximately $4 billion into a single project, the Jintang Undersea Tunnel, a name that is steadily gaining attention across the world. Undersea tunnels are not new. In fact, more than 20 such projects either exist or are planned globally. Some of the most iconic include the Channel Tunnel connecting the United Kingdom and France, Japan's Seikon Tunnel, and the Tsushima Strait Tunnel. Each of these stands as a testament to human ingenuity. Yet even among these giants, the Jintang Tunnel aims to push the limits further than ever before. According to official plans, Chinese engineers intend to complete this monumental structure in just 6 years. The announcement alone sent shockwaves through the global engineering community. Critics, particularly in the West, were quick to respond, many arguing that the project was unrealistic, even reckless. They claimed the technical challenges and sheer scale of such an undersea high-speed rail system were beyond what current engineering could reliably achieve. To them, it wasn't just difficult, it was impossible. But where others see limits, China sees a challenge. Rather than backing down, Chinese engineers have stepped forward with determination, ready to prove their capabilities not through words, but through results. For them, the Jintang Undersea Tunnel is more than a construction project. It's a statement of national engineering strength and technological ambition. This tunnel forms a critical section of the Yangzhou-Zhoushan Railway, a key transportation corridor designed to enhance connectivity and economic integration in the region. Yet, beneath its strategic importance lies a harsh reality. Every single meter of excavation beneath the sea presents enormous technical obstacles. The project will rely on a complex combination of bridge and tunnel construction methods. Stretching approximately 16.2 kilometers, the tunnel will descend to a maximum depth of 78 meters, with sections buried up to 50 meters beneath the seabed. Its diameter, an immense 14 meters, adds another layer of complexity. These dimensions are not just numbers, they represent unprecedented engineering challenges. To bring the structure together, engineers must execute multi-section tunnel docking deep beneath the sea. The scale of each segment, the precision required for alignment, and the environmental conditions involved place this project at the very top of global engineering difficulty. In both length and technical complexity, it is set to surpass all existing undersea tunnels. Once completed, it won't just break records, it will redefine them. And perhaps most notably, it will mark China's first undersea high-speed rail tunnel, opening a new chapter in transportation history. To tackle such a colossal undertaking, engineers are deploying a combination of advanced construction techniques, the open-cut method, shield tunneling, and traditional mining approaches. In shallow seabed areas where the soil is relatively soft, the open-cut method is used. This involves excavating directly from above, constructing the tunnel structure, and then restoring the surface. It's efficient, but only under the right conditions. When the seabed becomes harder, more unpredictable, or saturated with water, this method quickly reaches its limits. That's where the shield method comes in. Designed specifically for soft, water-bearing ground, this technique relies on massive tunnel boring machines, engineering giants capable of carving through the earth while maintaining structural stability. These machines operate with incredible precision, but they also bring their own set of challenges. At certain stages, the shield machine must be carefully dismantled without causing any damage and transported piece by piece to the next excavation section. And that is where the real complexity begins. As the tunnel boring machine pushes forward into layers of extremely soft silt, its cutting head begins the delicate task of excavation. Every rotation must be controlled with precision. At the same time, the massive steel shell of the shield machine braces against the surrounding ground, preventing collapse as it advances inch by inch beneath the seabed. Inside this moving fortress, the process never stops. Soil, gravel, and thick mud are continuously carved away and transported out through an intricate conveyor system, flowing like an underground river of debris, clearing the path for progress. But the deeper the machine moves, the more unpredictable the earth becomes. When the tunnel reaches zones of complex geology, where dense rock formations replace soft sediment, the strategy must change entirely. Here, brute force meets careful calculation. Engineers turn to the mining method, drilling into the rock and using controlled blasting to break through. This is no place for speed. Each section must be excavated gradually, with repeated drilling and precisely timed explosions. Too much force, and the structure could destabilize. Too little, and progress slows to a crawl. Every blast is a calculated risk, designed to balance efficiency with safety, because beneath the ocean, even a minor miscalculation can trigger catastrophic collapse. This is not the first time Chinese engineers have ventured beneath the sea. During the construction of the Hong Kong-Zhuhai-Macau Bridge, they employed a completely different approach, the immersed tube method. Massive tunnel segments were first constructed on land, then transported, submerged, and carefully joined together on the seabed, like pieces of an enormous puzzle. That project was groundbreaking. But the Jintang Undersea Tunnel takes the challenge to an entirely new level. Unlike the immersed tube approach, Jintang relies primarily on shield tunneling, and its undersea shield section alone extends nearly 10 kilometers longer than that of the Hong Kong-Zhuhai-Macau Bridge. By sheer scale, it stands poised to become the most extensive undersea tunnel ever attempted. And with that scale comes an exponential rise in difficulty. The engineering challenges here are not just greater, they are fundamentally different. Beyond construction methods, nature itself becomes a formidable adversary. One of the most critical factors is water pressure. At depths reaching 78 meters below the sea, the tunnel must withstand immense external force. The pressure on the seabed can reach up to 1.0 megapascals, a level that pushes the boundaries of current engineering capabilities. To put this into perspective, China's previous advanced tunneling technology could reliably handle pressures of only about 0.7 megapascals. Even during the construction of the Hong Kong-Zhuhai-Macau Bridge tunnel, the pressure peaked at approximately 0.8 megapascals. The Jintang project goes far beyond that. Before construction can fully proceed, engineers must achieve critical technological breakthroughs, developing new materials, stronger structural designs, and more resilient machinery capable of surviving these extreme underwater conditions. This is where innovation becomes not just important, but essential. If successful, the completion of the Jintang Undersea Tunnel will mark a defining moment in modern engineering. It won't simply be another infrastructure project, it will represent a leap forward in China's technological evolution, setting new global standards for what is possible beneath the ocean. And perhaps more importantly, it will send a clear message. For years, China has delivered one ambitious project after another, each one reshaping expectations. From the architectural scale of Beijing Daxing International Airport, to the engineering brilliance of the Hong Kong-Zhuhai-Macau Bridge, and now to this bold undersea high-speed rail tunnel, these achievements have steadily built a reputation that is difficult to challenge. In the face of technological barriers and external skepticism, Chinese engineers have continued to innovate, adapt, and overcome. Through persistence, ingenuity, and relentless effort, they have transformed obstacles into milestones. Today, China stands on the global stage not just as a participant, but as a leader in large-scale infrastructure. A nation often described as an infrastructure giant, driven by projects that redefine both scale and ambition. And now, with the Jintang Undersea Tunnel, the question is no longer whether it can be done, but just how far this journey of engineering ambition can go. As we continue to follow this extraordinary project, one thing becomes clear. This is more than construction. It's a story of vision, resilience, and the relentless pursuit of what once seemed impossible. So, what do you think? Will this undersea marvel truly reshape the future of transportation? Stay with us and experience the full story as it unfolds.